This is the 2019 Level 2 Waves exam, question 1. Right, so satellite communications can help isolated communities stay in touch, as well as improve signals for television radio communications. Typical receiver dish, as shown below, can be used for a range of waves in the electromagnetic spectrum. Receiver dish can be modelled using concave mirror and light rays. Although satellite dish is not truly concave, I think it's parabolic. A teacher decides to model the image formation using a concave mirror. So complete the ray diagram to show how parallel rays are reflected in concave mirrors in general. So you're going to need a ruler. I've got a bit of a rubbish ruler at the moment because I looked around the office and I couldn't find a good one. But anyway, so we are going to have, I'll do this ray here. Goes in parallel, out through the focal point. You got to have the arrows, and then this one here, in parallel. I'll move this up a little bit. Out through the focal point. There we go. Chuck the arrow on that, and then the last one, in parallel, out through the focal point. Hopefully that can be seen. Hopefully it's visible. Probably the arrow is probably just enough to give it away. I'll chisel that in. There we go. That's that one there. Right, next question. The students realise that in order to use a mirror for the model, they need to know its focal length. They place 3 centimetre high, so that is the HO, height of the object, is equal to 0.03 meters. I'm just doing everything in meters because that's how you should normally do. Lego toy 30 centimeters in front of the mirror, and determine, so 30, so this is DO, distance to the object. This is height of the object, distance to the object, 0.3 meters. And the image is 2 centimeters high, so HI is equal to 0.02 meters. Right, by determining the distance from the image to the mirror, calculate the focal length. So essentially we're going to find DI. DI equals question mark, and then we're going to try and find the focal length equals question mark. In your formula sheet, where is my formula sheet? You have this formula here, DI over DO equals HI over HO, or distance to image divided by distance to object is equal to, it's essentially equal to the magnification M, and it's always a positive, well, it's always, sometimes it's going to be a negative number because the images can be virtual. And then this will find your focal point. So we're going to find DI first using this formula here. So we'll go HI over HO times DO. So DI is equal to, what I'm going to do is times both sides. I'll just forget about that M, that it doesn't exist. We'll just pretend it's just this equation here we're going to look at. Times both sides by DO, that'll move it up. So we get, what do we got? DO times HI over HO, and that is going to be equal to 0.3 times 0.02 over, what's it? HO 0.03, and that equals 0.2 meters, and then formula here is 1 over F equals 1 over DO plus 1 over DI. I'm going to put brackets around this and inverse this whole lot. So essentially the the focal point is equal to, I'll put bracket 1 over DO plus 1 over DI bracket, and I'll go 1 divided by all of this. And the reason being is 1 over F is equal to F. So I go 1 over both sides, and it flips that F around to get regular F. And that's the focal point that I'm looking for, and that is going to be equal to 1 over bracket 1 over, what's DO? What is DO? 0.3. 3. And they're all positive distances because it's a mirror and everything's on. Oh, hold on. Ooh. is it in front of the focal point? Where's the focal point? We need to double check whether determine. Oh no, we're just trying to find the focal point. Yeah, they'll be all positive. They'll be all positive. Plus 1 over d. You know what's focal? Yeah, so this must be a real image, which means this must be on the left-hand side. Otherwise, they wouldn't be able to find the image at all. Yeah, just double checking. Otherwise, because if it's a virtual image, you end up with negative numbers. But let's just forget about that. DI is 0.2, and that equals 12 centimeters, as you can see. 0.12 meters. So the focal point is at 12 centimeters. There we go. Right, next question. What do we got? Draw 2 rays from the Lego toy object to locate the position of the image. Right, so we just got, what's this, a concave mirror? Yeah, it's a concave mirror, isn't it? Right, in parallel. Yeah. In parallel. And you just go to the back thing here, you don't go to there, you go to the very back. It's just like the way you do it. Out through the focal point. Out through there. And then we're going to go in through the focal point. Out parallel. There's there. In through the focal point. Out parallel. Hopefully that's parallel. Looks fairly parallel. You've got to put the arrows on them to show that the light is coming in on both sides. You have the arrows going in, arrows going out, and here is our image right there. And then and label the image. So I'm going to call this IMAGE. Hopefully that's sort of labeled enough, and then hopefully you can sort of see. So image bracket Lego toy, because that's what it is. What would be the effect on the position of the image by increasing the radius of curvature of the mirror? Explain your answer. So in your formula sheet, do they actually even give it? No, they don't. What do we got? It's not in there. This here is if you were to make this one a full big circle, 2 times the focal length is the center of the circle. So that would be the radius from the center of the circle to here. So 2 times the focal length gives you the radius of whatever circle you'd need to make the mirror. So if you increase the radius of curvature, you'd increase the focal point. So I'll say increasing. I might just pause, write it up, and then explain. Right, so I said increasing the radius of curvature increases the focal point. Using the diagram above, we can see that the image formed will be further from the mirror. It's because if the focal point shifts out, that means the rays would go, instead of going like that there and then bouncing back, they'd go like, if you went through the focal point here and then bounce back, your image would end up way back over here. So it'd end up further away. There is a formula, what is it? Radius, if it's going to be capital R, is equal to 2f. I'm not sure whether it's given. No, it's not in your formula sheet. But it's just something to remember. The students replace the mirror with a concave lens. Yeah. Place a Lego, complete the ray diagram to show the image produced. So this isn't too bad. Concave lenses, the lens means the light goes through. They're diverging lenses, so the light spreads out. So you still just go in parallel. Yeah, and then you go out through the focal point because the light diverges. Diverge just means spread apart. It spreads apart, spreads out like that. Right, that's one way you can do it. There's another way, is you go in through the pole of the mirror. Pole just means the center of the mirror. The light just goes straight through, so it's kind of like a cheeky way to do it. In through the pole of the mirror, the light just goes straight through. I'll chuck some arrows to show this direction. And you can see there'd be you'd never have an image formed over here because the light rays never meet up. So what you have to do is you have to backtrack this outgoing ray, if I can just line my ruler up, backtrack this with dots, and then we have our image. There we go. And does it want to label it? No, it doesn't ask to label it. This is our image formed. It is virtual because you could never if you had a screen over here, you could never project this image onto a screen because it would never go in focus. So it's virtual, up, right, GHT, and it's diminished, because it's smaller. I think that's really about it.